All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good to hear. Last week before spring break. Hopefully, we can all make it through and have a good spring break after this because it's been a while. Okay, all right. So plan for today. So we started our discussion last Thursday about finite element forms. So we're going to continue with that discussion. So this is where you're going to see a lot of things kind of come full circle. So we spent quite a bit of time talking about boundary value problems, strong form, weak forms, but we didn't really make the connection back to finite element problems, which is what this class is all about. And so we'll make that connection today. You'll kind of see where it all connects, and we'll hopefully get through an example today as well. Okay. All right. Any questions I can answer before we get started for today? Okay. Okay. All right. So let's go ahead and pick up where we left off. Okay. So topic for today is finite element forms. Oh, by the way, I did post a homework assignment on this stuff. It is on Canvas right now. So unfortunately, with the timing of the spring break, I did have to assign it, this week. But just know that, I did bake in some extra time after the spring break for you to work on it. So it's not going to be due until after spring break, but it's not going to be due until Sunday. I believe it's April 12th. So the spring break goes up until April 5th. Our first day back is April 6th. So you'll have that first week when we come back to work on it, in addition to this week, of course. And so you should be able to do a lot of it actually already. It's really just the last problem on the homework that you may need some extra time on based on what we cover this week. Okay. Okay. All right. So let's go ahead and pick up where we left off. So we're talking about finite element forms. Okay. All right. So before we kind of jump back into kind of the weeds of the derivation, let's kind of take a step back and kind of talk about kind of what our ultimate goal is, or kind of what our approach is going to be. Okay. So the big difference between this section of the class and the first section of the class on direct stiffness method is we are working now on kind of what I call general boundary value problems. And where boundary value problems are given by I like to give it the acronym BVP. Okay. Okay. So remember, boundary value problems, they have three components. And so on the one hand, we have our governing equation. Next, we have our geometry or our domain. Okay. And three, we have our boundary conditions. Okay. Okay. So we were introduced to this concept, even before the midterm exam, right? And what we said was that we have what we call traditional ways of solving this, which are the strong and weak form solutions. Right. So those are kind of more traditional ways to solve this problem. I guess you could say the strong form is kind of the really traditional way. That's probably how you solved these in the past before. Okay. But what we're seeking now is we want to be able to solve these in a finite element using a finite element technique. Okay. Where a finite element technique is, basically using an approach that we use in our direct stiffness method, right? And so that involves, element stiffness matrices, okay, assembly, boundary conditions, okay, all kind of leading up to the to kind of the use of a large linear system of equations. Okay. Right. Essentially, the one way that you can think about this is that, we're basically using the finite element technique to take a system that's governed by a differential equation and instead formulate it as a system governed by a linear set of algebraic equations. Okay. So we're going from differential equation to algebraic system of equations. Okay. Okay. So the way that we're going to do this is the following, right? So let's say that, in a one-dimensional case, right? We have your domain here, right? We have our governing equation on this domain, and we have the boundary conditions. Okay. What we're going to do is we're going to take this domain where, before when we did strong and weak form solutions, we considered this domain as kind of one domain, and we solve for the solution everywhere. Okay. What we're going to do instead is we're going to break up this domain into several elements. Okay. Okay. You can have a lot of elements. You can have, only two elements. Technically, you can have just one element. Okay. Where each element here is going to have its own element stiffness matrix using the methods that we're going to talk about today. Okay. Right. So element A, element B. So in this case, we have three elements, right? Each element okay. Each element in our domain that we kind of choose will have its own element stiffness matrix, where the values of the element stiffness matrix will depend on the underlying boundary value problem. Okay. Right. So that's kind of the main difference in terms of what we're doing now versus kind of what we did before the midterm, is the way that we're going to compute the element stiffness matrices is going to be much different than before. Okay. So this is kind of the step that we'll focus on, because the other steps are more or less the same. There's a little bit of nuance in how we do the Neumann boundary conditions, and so we don't just add those in post. Now we have to kind of account for it, while assembling our element stiffness matrices. So, but for the most part, the biggest difference compared to what we're doing in the second half of the class and the first half of the class is how we do the element stiffness matrices. Okay. And just be assured, just because I know there's maybe a little bit of trauma from the first midterm, that the element stiffness matrices that we're going to get from these problems are going to be much smaller than they were before. Okay, and so for our 1D problems, our element stiffness matrices they're all going to be 2 by 2. Okay, and then eventually, we're going to get to 2D problems, and even in 2D problems, we're going to focus mostly on either triangle elements or quadrilateral elements. And so those are going to be either 3 by 3 or at most 4 by 4 for the element stiffness matrices. Okay, so nothing too crazy. Okay, right. And we're not going to have systems with a bajillion different elements, right? And so these problems are smaller. So I promise that to many of you after the first midterm. But these problems are smaller just because the matrices are just naturally much smaller than before. Okay. Okay, so that's kind of where we're going, and so I wanted to kind of take a second to kind of go over this this general approach, before we kind of jump back into the weeds of the details. Okay, because I think what can happen with these types of problems and with these concepts, it's very easy to get lost in the details, and then it's hard to kind of remember exactly the reason we're doing this or kind of the whole purpose of this whole thing. Okay, so before we, I know we kind of stopped right in the middle of the derivation last time. Before we jump back into it, I wanted to kind of go over this general approach, just so you kind of know exactly what we're doing. Okay. Any questions on this? Okay. All right. So let's jump back into the derivation of the element stiffness matrix for 1D boundary value problem. Okay. All right. So where we left off, let's kind of summarize what we've done so far, right? So when we're deriving these element stiffness matrices, we're essentially working off the weak form of the solution, or weak form of the boundary value problem. Okay. And so when we're working with the weak form, typically we assume a form of the solution. So we're finding an approximate solution to the weak form, right? And so in our particular case, we're doing the simplest possible polynomial that we can do, which is a linear function. Okay. Right. And then what we did with that linear solution was that we enforced some conditions on that solution to make sure that we have continuity of the solution in between different elements. Right? Because what we said is that in order for our solution to be continuous from element to element, they have to have the same matching nodal solution, right? Because the node is shared between two elements. Okay. And what that led us to was the following expression here. This is right where we cut off, right? So we always says that the function for our solution UE of x is equal to n1 of x times u1 plus n2 of x times u2. Okay. Where u1, u2, these are the nodal solutions. Right? So those are the solutions to our boundary value problem at the nodes of our element. Okay. And then n1, n2, remember, these are our shape functions. Right? Where shape functions, you can consider them, for all intents and purposes, to be interpolation functions that have the same polynomial order as our original assumption. Okay. So since for these problems, we're assuming a linear solution, these shape functions are also linear functions. Okay. All right. And so just because they'll serve our purpose, let me go ahead and write out their expressions again. Okay. So the expressions for the shape functions n1 is equal to x minus x2 divided by x1 minus x2. And then n2 of x is equal to x1 minus x divided by x1 minus x2. Okay, good. All right, one other thing that we'll compute right now, just because we'll use it later, is let's compute the derivatives of these shape functions as well. Okay. Okay. And so to take the derivatives of these are simple linear functions. So we're just going to basically just take the derivative of the x term. So we have dn1 dx, okay, is equal to, we take the derivative of that, we just end up with just the constant 1 divided by x1 minus x2, and then dn2 dx is equal to 1 divided by x2 minus x1. Right? So for dn2 dx, I just took the negative from up top and just applied it to the bottom. So I swapped the order of the difference. Okay. All right. So the reason I did that is, we're very quickly going to come to a situation where, we're going to take the derivative of our solution function, right? And so if you take the derivative of UE, so due dx, right? So in our situation here, U1 and U2, right, the nodal solutions, those do not depend on x. For all intents and purposes, those are constants, right? And so if we were to take the derivative of our solution function, the only parts of our solution here that actually take the derivative are going to be the shape functions, right? So due dx is going to be equal to dn1 dx multiplied by u1 plus dn2 dx multiplied by u2. Okay. All right, so we've kind of defined a lot of expressions here, a lot of terms. Let's actually get to use this. Okay. So the next step in this procedure is to actually take these expressions, right, with shape functions and everything, and actually plug that into the weak form of our boundary value problem. Okay, but before we do that, are there any questions just on anything here? Okay. All right. So let's go ahead and plug in for this. Okay. Now, you know, the way we're going to use our weak form here is we're only going to integrate our weak form across the length of our element here. Okay. Because if you go back to our weak form, right? So this is just a pure weak form, right? So we have integral from 0 to L of dw dx e times a du dx is equal to integral from 0 to L of w of x v of x dx plus our Neumann boundary condition term. So this is w times a times your Neumann value t bar, right? So t bar would be some kind of applied compression or applied tension. Okay, and we evaluate this at the location of the Neumann boundary condition, right? So x is equal to lambda or gamma h, excuse me. Okay. Okay. So in our traditional weak form here, we're integrating across our entire domain, right? So our domain is defined from 0 to L, right? But we only want to apply this weak form for our particular element. So instead of integrating from 0 to L, we're going to integrate from the bounds of our element, which is x1 to x2. Okay. Right? And so I'm going to change those bounds from 0 to L to x1, x2. So integral x1 to x2 dw dx times e times a du dx is equal to integral from x1 to x2 w of x v of x dx plus w times a times t bar x is equal to lambda h, gamma h. Okay. So the reason we can do this is, we just want to focus on just one, honestly, we just want to focus on one element. But, we can make use of the fact where, our original weak form, you can consider that, we're breaking up this original integral into several different elemental integrals. Okay. And so to go from here to here, right, we're going to break up original integral okay. So we're essentially taking advantage of the fact that, if you have an integral across an entire domain, right? And so let me kind of illustrate that out. So this will be kind of an aside here. Okay. Right. So let's say you have your domain from 0 to L like this, right? And let's say you have an integral from 0 to L of something dx, right? You can take that same domain and break it up into lots of different subdomains, right? Right, so let's say this is x0, x1, x2, x3, x4, x5, right? So we can take advantage of the fact that, one integral from 0 to L is equal to the exact same integrals, or is equal to, in this case, 5 different integrals across each of our subdomains, right? So this is equal to x integral from x0 to x1 dot 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 dx plus integral from x1 to x2 dot 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 dx plus integral from x2 to x3 dot 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 dx. Okay. Right. So all we're doing is we're basically taking our original weak form integral here and then only integrating across an entire for just one element, knowing the fact that we're going to take this result and just add it together to the elemental integrals for all the other elements that we have. Okay. So it's not that we're neglecting the rest of the domain here. We're just focusing on just one element at a time, and then we're going to repeat this process for all the different elements. Okay. But what you'll see is that for this particular element, or for the kind of way that we structure these problems, doing this work for just one element, we can take that result and kind of generalize it to the other elements to kind of save us some work in the future. Okay. So on the one hand, this looks like a lot of work where we're doing a lot of these different integrals here, but it ends up being not that much because there's a lot of the same patterns kind of repeat, especially for the element stiffness matrices. Okay. All right. So let's go ahead and plug in for this. Okay. Okay. All right. So remember, right? We have these expressions in our weak form here. So we have dw dx, we have du dx, w of x here, okay? W. Okay. So the key to evaluating this integral is to, plug in expressions for dw dx and du dx. Okay? So before we move forward with any integration and with any calculations, we need to plug in expressions for du and dw, okay? For this particular element. Okay. Now, luckily for us, we've already done the work to come up with the expressions for u at least, right? We have that right here, right? So u, we know it's just n1 of x times u1 plus n2 of x times u2. And in fact, we also have the derivative as well, right? So due dx is equal to dn1 dx u1 plus dn2 x dx u times u2, okay? Right, so we know du dx is equal to dn1 dx u1 plus dn2 dx u2. Okay. Okay. Now I'm going to do something a little bit strange here. So I'm going to take this summation here and put it in vector form, right? Because ultimately what we want from this is we want an element stiffness matrix. And so in order to get it, one way to get a matrix is to take vectors. Okay. So one way that we can do this is we can take basically the row vector dn1 dx and dn2 dx, okay? Multiply that by u1, u2, okay? So we're taking a row vector multiplied by a column vector, which essentially is a dot product, right? But we want to put it in this form so that we can, actually get a matrix from this, okay? Okay, now that's our expression for u, right? But we also need to plug in for w as well, because that w, that weighting function is also part of our weak form. Okay. Now remember, our weighting function here is kind of a special thing. Where remember, we always assume that our weighting function has the same functional form as our solution. Right, so our weighting function, if you think back to when we did weak form solutions, right, the way we defined w of x was that it had the same functional form as u of x, with some additional requirements, right? So we also require that they disappear at the Dirichlet boundary conditions, okay? But the only relevant part for now is that it has the same form of U, okay? Now, what that means is that we can actually use the same, we can use the same shape functions to define W of X as U of X. Okay. All right, so that means W of X is going to be equal to N1 of X times W1 plus N2 of X times W2, okay? Where W1, W2 here, that is the nodal values for our weighting function, okay? In the end, we're not going to care about them, right? So if you think back to our weak form example that we did last Thursday, ultimately we didn't care what W1, W2 were, but we do need them for our solution, right? So we do need to put a placeholder there, essentially. Okay. And we can also form its derivative because we do need that for our weak form as well. And so just like U, this can be dn1 dx times W1 plus dn2 dx times W2. Okay. And so once again, we're going to put these in vector form just to, just to kind of make it so we can get matrices and vectors. Okay. Because essentially these two quantities here they're essentially just dot products. Okay. And so to put this in vector form, we're going to do row vector of W1, W2 multiplied by column vector N1, N2. Okay. And then for the derivative, we have a row vector W1, W2 multiplied by column vector dn1 dx and then dn2 dx. Now, you might be wondering, right? So if you kind of notice here, you compare our vector expressions for dw dx and du dx, right? You can see that I've kind of swapped the two vectors, right? So for du dx, I have the shape functions there as our row vector, but for our weighting function, I have the w coefficients, w1, w2, that is our row vector instead, okay? Now, this is just convention, right? And so convention just state that for the weighting function, you make the column vector equal to the shape functions. That's mostly just that we can get a nice linear system out of it. But it's fairly arbitrary. And so, as long as you use one convention for the weighting function and a different convention for the solution, you're going to end up with the same thing. Okay, it's just that the most classical way to do this is like this. Okay. Okay. All right. So now that we have all these expressions here, we are ready to plug in. Okay. So basically everything that I've circled in pink here, and I'll highlight it in yellow again as well. Okay. Right. So essentially what we're going to do is we're going to take our vector expressions for these quantities and just plug it in and just kind of work through the algebra from there. Okay, so it's going to get a little bit messy from here. So before we start, are there any questions on anything up to this point? Okay, all right. So let's go ahead and get rolling. Okay, so we're going to go ahead and oops. Let's go ahead and plug these in. Okay. All right, so we do all that. We plug it in. We get integral from x1 to x2 of w1, w2 multiplied by column vector dn1 dx, dn2 dx. Okay. We have E times A, right? Typically, E and A, the Young's modulus and the cross-sectional area, are constant, right? So usually we can factor them out. But this expression here also accounts for the fact where maybe we have a tapering rod. where our cross-sectional area is going to differ, right? And so we'll leave them in the integral, but just know that if they're constant, you can bring them up. Okay. All right, so now we have the contribution from du dx. And so that is a row vector dn1 dx, dn2 dx, multiplied by the column vector u1, u2, okay, dx. Right, so that is the first term in our weak form. So that's this integral right here. Okay. All right, and so this is equal to, right? Next, we're going to plug in for the source terms. So we're going to have integral from x1 to x2 of w of x. So w of x we know is w1, w2 multiplied by n1, n2, b of x dx. Okay. Plus, we have our, we have our Neumann boundary condition term. Okay. Okay. So once again, we also have w1, w2 multiplied by n1, n2 multiplied by a times t bar. Okay. And we're only evaluating this at the location of the Neumann boundary. Okay. Actually, small thing. Sorry. So this last n1, n2 should be a column vector, just so it's consistent with our weighting function. Okay, so we got vectors, shape functions just flying all over the place, right? And so there's a lot to unpack here, right? And so there's we're going to spend the next few minutes doing that. But all we've done essentially here is we've taken our expressions for our solution derivative and our weighting function and plugged that into our weak form to get this expression here. Okay. Now I'm gonna kind of tackle these terms one by one, just because there's again a lot to unpack. So let's start with the first integral here, because this integral here, this is going to form our basis for our element stiffness matrix. Okay. So we'll come back to the other two integrals a bit later, but let's just focus on this one first for now. Okay. So first thing I'll note here is that, even though e times a, we're going to leave it within the integral, the nodal values we know are actually going to be constants. Okay. So w1, w2, u1, and u2 are all constants. Okay, so let's go ahead and factor those out of the integral. So we have w1, w2 integral from x1 to x2 of dn1 dx, dn2 dx multiplied by e times a times the row vector dn1 dx, dn2 dx, dx, okay? And then we're multiplying that by a column vector u1, u2. All right. So if you do the vector-vector multiplication, we have a very interesting one here, because normally, you see two vectors multiplied by each other, you're usually doing like the dot product, but this one we're actually doing what's called an outer product, because if you look at this, the dimensions of this matrix, the first one is a 2 by 1, right? So we have two rows and one column, and the dimensions of the second matrix is 1 by 2, right? And so you multiply these two matrices together, right? first of all, we see that we can do it because the inner dimensions are the same, right? And the result that we get is a 2 by 2 matrix, okay? And so if you write it out, right, you get the following. You have W1, W2 times integral x1 to x2, right? We have a 2 by 2 matrix here, and so the 2 by 2 matrix is dn1 dx, dn1 dx, okay. dn1 dx, dn2 dx. Same thing in the bottom left. So dn2 dx, dn1 dx, right? And the bottom right, we have dn2 dx, dn2 dx. Okay. Right. And then we're still multiplying by e times a dx. Okay. So this expression here, right, specifically everything except for the nodal values, right? It doesn't quite look like it just because we still have an integral to do, but this right here, this is our element stiffness matrix. In particular, it's the element stiffness matrix for 1D elasticity, right? So we're doing elasticity because remember, we see the Young's modulus in there. And so Young's modulus is kind of a giveaway that we're doing elasticity. Okay. Okay, so to evaluate this matrix, where you need to compute the shape function derivatives, right? So n1, n2, multiply them together into the matrix, and we need to integrate it together with e times a, okay? Now that seems like a lot of work, right? And especially if you have functions of x, but remember, our shape function derivatives for our linear element are constants. Okay? Right, so both dn1 dx and dn2 dx, right? Remember, these are constants. Okay. Right, so taking the integral is actually not going to be too bad because we're just integrating constants essentially. Okay, good. All right, so that's our expression for the element stiffness matrix. It's a little bit hard to kind of move on from here just because we have to plug in for E times A, but we'll definitely do this in the first example that we do. Okay. Any questions on anything up to this point here? Okay, good. All right, so that's the first integral in our expression there, right? And so that gives us our element stiffness matrix. Let's look at all the other terms in this expression now as well. So this part is actually quite a bit unique compared to how we did our direct stiffness problems, right? Because when we did direct stiffness, we didn't really have a concept of an element forcing vector. We had element stiffness matrix, but no element forcing vector. Okay. So let's go over that now. Okay. So the element forcing vector, like I mentioned, is something we've mostly neglected up until this point. Okay. But it's always been there. It's just that we've kind of just applied it in a different way in direct stiffness. Okay. So every element, right? Every element in a finite element problem always has an element stiffness matrix and an element forcing vector that describes the physics of that particular element. Okay. So for every element, we essentially have the following, right? So let's say we have an element like this, x1, x2, u1, u2, right? Right, we're always going to get a system that looks like this. We have an element stiffness matrix, okay? So usually we call that K, okay? Times u1, u2. And then we have our element forcing vector, f1, f2, okay? Where f1, f2, like I said, we've usually neglected this, but this is present for every element here, okay? Now, this element forcing vector, it's basically going to tell us the effect of any external effects on our element. And so in particular, we're looking at the effects from the body forcing term, which for our case is b of x. And capture any effect from the Neumann boundary condition T bar. Okay. Right. So the Dirichlet boundary condition will apply that in the same way that we've done before. But the way that we do the Neumann boundary condition, and now we have this body forcing term that we never had before. The way that we're going to account for it is a little bit different. Okay. Okay. And so in fact, knowing that these are the two effects that we are accounting for, that actually perfectly encapsulates the two integrals that we need to evaluate, right? And so the first integral that goes into the element forcing vector, okay, is the integral of the body forcing term. So that's integral from x1 to x2, w of x times b of x dx. Okay. So we've already plugged in for w of x, right? And so let's go ahead and plug that expression in. So that's w1, w2, integral from x1 to x2 of n1 of x, n2 of x, b of x, dx. Okay. Okay. Now, I put a box around this expression here because we can't really take it any further because we can't evaluate any integrals until we plug in an expression for b of x, right? And so depending on the form of b of x, or maybe b of x just doesn't exist, maybe we don't even have a body forcing term, this expression we can't, it's going to depend on the problem. Okay. But just know that we are going to have the contribution. And I believe the example that we're going to do actually does have a forcing term. I think so. Yes, it does. Okay. Okay. All right. So that's one element of our element forcing vector. Okay. Now let's look at the other term. Right. The other term was our Neumann boundary condition, which was given by the following. So you have W times A times T bar evaluated at X is equal to lambda H. Okay. All right. Once again, we're going to plug in for W of X here. Right. So W of X is going to be W1, W2 multiplied by N1 of N2 times A times T bar. Evaluate X is equal to lambda H. Okay. Okay, so this term is special here. So, if you've noticed, this is the only term that we're looking at here that's not an integral, okay? And so it's important to remember that we're only going to evaluate this if there is a Neumann boundary condition. So honestly, for most of the time, you're going to be looking at elements. There's going to be no Neumann boundary condition present, right? You're either looking at an internal element where there's no Neumann boundary condition, or you're looking at an element where there's a Dirichlet boundary condition present. And so, in that case, you don't evaluate it either. Okay. Now, if you do have a Neumann boundary condition, you need to make note of which side the Neumann boundary condition is being applied to. Okay. Right? So you can't have a Neumann boundary condition that occurs in the middle of the element. It's either going to be on the left side at x1 or the right side at x2. And that's important because that actually affects the value of our shape functions, right? N1, N2. And so let's say that your Neumann boundary condition is on the left side, so it's at x1. Okay. And so in that situation, your N1 of x1 or N2 of x1, right? Remember the properties for the shape functions. When you're evaluating the shape function at the matching node, you get 1. You evaluate the shape function at the opposite node, you get 0. Okay. And so this vector here, this n1, n2, right? Right, it's either going to be 1, 0 if the Neumann boundary condition is on the left, or if the Neumann boundary condition is on the right. Right? So we have Neumann BC at x2. Okay. Then n1 of x2 and 2 of x2 is equal to 0, 1. Okay. So it's a lot of information, I know. So there's a lot of details with this methodology. Okay. But I think once we do an example, I think it'll become a bit more clear. I think it'll become a bit more familiar with what we've done. The only difference now is that we're computing our element stiffness matrices a different way, and our element forcing vector we have to compute as well. Okay. But our element forcing vector is essentially going to be the summation of both of these contributions here. Right. So we have one contribution from the body force, another contribution from the Neumann boundary condition. Okay, any questions on this before we jump into an example finally? Okay, all right, so let's go ahead and do an example, right? So hopefully it'll kind of all come together with this example here. Okay, so let's consider this one-dimensional elasticity problem with 2 elements. Okay, so let's draw our boundary value problem first, and then we'll show how we're going to break it up into elements. Okay. So we're going to look at kind of a very simple truss bar here. So we have a truss bar that's just like that. Okay. Obviously, it's fixed on the left-hand side. On the right-hand side, we're going to apply a compressive pressure. Okay. right? And so on the right-hand side, we have T bar is equal to minus 5 Pascal. The total length of the bar is going to be 20 meters. Okay. And then in addition, we're gonna have a body forcing term. So let's say we have kind of a consistent kind of force that's being applied throughout the body of the bar. Okay. Right, so we can say that B of x is equal to 2 Newton per meter. So just a constant body force. Okay. Okay. And then as for properties of the bar, we'll say the Young's modulus is a constant. So we'll say Young's modulus is 5,000 Pascal. Okay. So it's made of some uniform material with the consistent Young's modulus. But we're going to say that our rod here is actually going to flare out. Okay. And so so I didn't illustrate it here just because I suck at drawing. But we're going to say that the area is actually going to be a function of x. Okay. So our area is going to change according to the following functions. We have area of x is equal to 1 plus x squared divided by 400. Okay, so that's something that we haven't seen before, right? So, all of our truss bars we've seen before have had consistent area. Now we have one that's kind of flaring out and kind of increasing in area as you go along the bar according to a quadratic function. Okay. Okay, so what we want to do is we want to compute the finite element solution to this problem. Okay. All right, so we're going to use kind of the element stiffness matrices and element forcing vectors that we've been discussing. Okay, and we're going to do it on a two-element domain here. Right? And so it's actually going to be a skewed domain. And so our elements here are not going to be uniform. Okay, so this is going to be element 1. This is going to be element 2, right? Obviously, element 2 is much bigger than element 1. Okay. We have our 3 nodes in this case, x1, x2, x3. So x1 in this case is going to be 0, x2 is going to be 5, and x3, that's going to be at the end of the bar, which is going to be 20. Okay. And then each of those nodes have their own corresponding nodal values. Okay. U1, U2, and U. Okay, so that's the setup for the problem. So essentially, we're going to run through the same process twice. We're going to run through this process of computing element stiffness matrices, element forcing vectors. We're going to do that first for element 1, that goes from 0 to 5. And then we're going to do it again for element 2, which goes from 5 to 20. Okay. All right, any questions just on the setup for the problem? Yes.
What's the bar? Is that bar T or is
This thing at the end right here, that's T bar. So that's an applied tension. So that's our Neumann boundary condition, basically. Okay. Yep. Mm-hmm. All right, question. Question. So the way the elements were spaced out is given. Yes. So for this particular problem, the spacing of the elements was given. Yeah. Just so that we can all kind of be on the same page. So normally, for these problems, and I think for the homeworks, for the most part, I give you evenly spaced elements. It's just that for this one, just to kind of give you a different look, we're doing them separately. Yeah, or the elements are different sizes. Mm-hmm.
Question.
Yes.
From a practical real world perspective, our elements, will they always be equally spaced, or will there be cases like this?
Yeah, no, it's a great question. I would say practically, unless you have a good reason, most of the time having a uniform mesh is pretty is what you want, just because it makes the calculations easier. Now, you may add some mesh refinement, and so there may be areas where you want to have smaller elements. Mm-hmm. And so, usually for structural mechanics, those will be areas where we have stress concentration. So kind of ahead of time that you're going to have stress concentrated in this particular area. You probably want to have greater mesh density there. But if you don't have any reason to believe that, just a uniform mesh is usually fine.
Okay.
Yeah, good question. All right, any other questions on the setup of the problem? Okay, all right, so let's go ahead and move on with the solution. So let's start with element one. Okay, so we're going to compute the element stiffness matrix first. Okay. Okay, so our formula for the element stiffness matrix looks like the following, right? And just note that for element one here, x1 is 0 and x2 is 5. Okay. So our element stiffness matrix is we're going to take the integral from 0 to 5 of, we have our 2 by 2 matrix that we had up there. So dn1 dx, dn1 dx, dn1 dx, dn2 dx, dn2 dx, dn1 dx. Trust me, it takes longer to write dn dx than it is to actually compute it. Right? And dn2 dx, dn2 dx. Okay. Okay, so we have our 2 by 2 matrix there. Okay. Multiplied by E times A dx. Okay. Okay. All right, so I'm not writing that again. That takes forever to write. It's a lot of derivatives there. Okay? Because what we see is that once we plug in for the shape function derivatives, it actually simplifies quite a bit, right? Because what do we know, right? So if you look back in your notes, I think that we covered this maybe like 45 minutes ago, right? We had expressions for dn1 dx and dn2 dx because we were using our linear shape function, right? So dn1 dx was 1 divided by x1 minus x2, and dn2 dx is simply 1 divided by x2 minus x1. Okay. All right, so we plug in x1, x2. We actually know those for this particular element. x1 is 0, x2 is 5. So that means dn1 dx is a minus 1/5, and dn2 dx is a positive 1/5. All right, and so their product, and so you can see that all the products are just, one multiplied by the other. And so their product is going to be 1 divided by 25. Okay, so that's 5 times 25, 5 times 5. Okay. Okay, so that's pretty straightforward. Next thing that we can plug in is we can plug in for E, because remember, E is a constant. Okay, so for this particular problem, E is 5,000. So let's go ahead and plug in for that. Okay. Right. And then for A is actually the only expression here that we have to integrate because everything else is a constant, right? So A, we're just going to plug in this expression here, 1 plus x squared divided by 400. Okay. Okay. All right. So that is to say that, most of these things are going to simplify quite a bit. Okay. And so, just knowing the fact that everything here in the matrix is going to be 1 over 25, in this case, minus 1 over 25. Okay. And we're going to multiply that by 5,000, right? And the fact that it's all constant means that we can take it out of the integral. Okay. And so we have 5,000 divided by 25, that is 200. Okay. So we have a matrix here that is 200 minus 200 minus 200, 200. Okay. Integral from 0 to 5 of our A function here, which is just 1 plus x squared divided by 400 dx. Okay. All right, so that is a fairly straightforward integral to do. Not super trivial, but not the worst at the same time, right? All right, so our constant matrix is still there. Okay. We take the integral, that becomes x plus x cubed divided by 1200. Okay. Evaluated from 0 to 5. And so when you evaluate that from 0 to 5, you just get some constant there. Unfortunately, it's not a very nice number. You get 5 plus 5 cubed over 1200. And so I think the operative thing there is 5 cubed over 1200, which is 125 over 1200. Right. So I'm just going to give you the final result, but just know that you can verify this yourself. Right. And so the element stiffness matrix, after you multiply that throughout the entire matrix here, you get 1020.83 minus 1020.83 minus 1020.83 and 1020.83. Okay. Yes.
Because I kind of missed it well, right? Where did the 200 come from?
Yeah, so the 200 was a result of the fact that, all of our shape function derivatives here are going to be 1 over 5 or minus 1 over 5. And so you take their product, they become 1 over 25. And then our Young's modulus was 5,000. So that's 5,000 divided by 25. Yeah. All right, question. So how many sig figs or decimals should be used for the next exam? So usually on the exam, I try to give you guys kind of nice numbers where you don't need that many sig figs. But usually two decimal points, 2 points after two figures after the decimal point is usually fine for me. Yeah. Yep. All right. Any other questions on this part here? Okay. All right. So that is the element stiffness matrix for element 1. Now let's do the element forcing vector. Okay, so remember the element forcing vector in general has 2 contributions. So we have one contribution from the body force. That's always going to be present if you have a body forcing term. So there's no decision making there. And we have a contribution from the Neumann boundary condition. Okay. So we have a body force contribution plus a Neumann BC contribution. But remember, we only evaluate the Neumann boundary condition if this particular element has a Neumann boundary condition attached to it. Okay. And so the first question you should always ask when you're evaluating element forcing vectors is, where is the Neumann boundary condition, and do I have a contribution on this element? Okay, so to answer that question, we do need to go back to the problem. Okay, right? And so our problem is given by this here, right? And so we know that the Neumann boundary condition is being applied on the right-hand side of the domain. Okay, it's being applied at the right hand. If we look at element 1, right? Element 1 is this portion of the geometry right here, which is the portion that's connected to the fixed wall up into a midpoint, not really the midpoint, but somewhere in the middle of the domain. Okay. And so for this particular element here, we do not have any contribution to the Neumann boundary condition, because the Neumann boundary condition is applied right here. Okay. So when we do the same exercise for element 2, we are going to have a contribution from the Neumann boundary condition there, but for element 1, we don't have any contribution. Okay. And so we come back down here and we say, does element 1 have a Neumann boundary condition? No. Okay. And so for element 1, we are not going to have that contribution just because we don't have a Neumann boundary condition. Okay. And so the only thing we're going to evaluate here is the body forcing term. Okay. So the body force integral here, this is integral from 0 to 5 of n1 of x and 2 of x multiplied by b of x dx. Okay. Okay. All right, so let's go ahead and plug in all of our values here. So remember, n1 of x, let me just kind of write it down here just because it's been a while, right? n1 of x is equal to x minus x2 divided by x1 minus x2, and n2 of x is equal to x1 minus x divided by x1 minus x2, okay? Now, these are actually functions of x, right? So we didn't take their derivative, so we do have to integrate them, okay? And our b of x for this particular problem is just a flat 2, okay? Okay, so let's go ahead and plug in for all of those expressions there. And let's make note that, both n1 and n2 have an x1 over x2. So I'm just going to pull that out of the integral as well, okay? Okay, so we go ahead and we plug in for that. We have 2 divided by x1 minus x2, integral from 0 to 5 of x minus x2 and x1 minus x dx. Question?
Should N2 be on the first integral?
N1 is on the first integral.
That should be N2, right?
So N1 is x minus x2. This one right here.
Above that.
Oh, yes. Oh, thank you. Yes. This should be N2. Yep. All right, and so at this point, we can plug in for x1, x2. So x1 for this element is 0, x2 is 5. So let's go ahead and plug in for that. And so we have 2 divided by 0 minus 5, and so that is a minus 2/5 integral from 0 to 5 of x minus 5 and 0 minus x, which is just minus x dx. Okay. All right. So we have a fairly simple integral to do, but it is, we do have to do 2. So it's kind of 2 for the price of 1 here. Okay. So we go ahead and evaluate this integral. We get minus 2/5 multiplied by x squared divided by 2 minus 5x, and then minus x squared divided by 2, evaluated from 0 to 5. Okay. Okay. So we can simply plug in the integration bounds here. So up top, we have 25 over 2 minus 25. And so that's going to give us a minus 25 over 2. And then on the bottom entry, we have a minus 25 over 2. Okay. And so a minus 2/5 times minus 25 over 2 minus 25 over 2. Okay. All right. And so we multiply this out. We get 5, 5. All right, and so that is our solution here. And so let's go ahead and plug those in, right? And so our elemental system for element 1, okay, is the following. So first we have our element stiffness matrix, which is 1020.83 minus 1020.83 minus 1020.83, 1020.83, okay? So just like we did in our direct stiffness problems, remember, we have to indicate which degrees of freedom are being acted on by this element, okay? So for this particular element, we're being acted on by U1 and U2, okay? So those are our degrees of freedom. And this is set equal to our element forcing vector that we just determined, which is 5 and 5. Okay. All right, and so that's the basic procedure, right? And so I know, we went kind of slow here just because, this is our first time. But when we come back on Thursday, we'll do kind of the same thing again for the second element, okay? So it is a little bit unfortunate. We're kind of cutting the example kind of midway through. But I think it's kind of a good review as well, just because, we'll get a chance to kind of do the exact same thing just with the other element there, okay? All right, so we'll finish this up on Thursday. And I think that'll be and then there's just a few more topics after that for finite element forms. And so, we're kind of ending the class before the spring break kind of on a good note. And so by the time we finish Thursday, you should have everything you need to do your homework. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Thursday. Oh, and so today is the last day I'm bringing the exams to class, and so if you haven't picked up your exam, please pick it up. But if you don't pick it up after today, you have to come to my office to pick it up. Yep.
The other one, the open form thing, did you go over that in the previous lecture?
Yep. Yeah. So So it actually took us like 2.5 lectures to do the open form stuff. And so if you go back to the lecture recordings, so if you go back to like Wednesday of week 8, that's when we first introduced Linux, and then the following Monday we did the open form stuff, and then we finished up the post processing on Linux.
We have the things,
Okay, yeah. Once the installation, I think is definitely the hard part. So once you have it installed, the activity goes pretty quick. Okay. All right, Lewis, any final questions before I close it up? All right, see you Thursday.